session is session number 7 for the Machine Learning Study Group webinar series, An Introduction to Neural Networks and Deep Learning, by our hosts, Julia, data science intern, and Shruthi, software engineer at Motork. And again, our next session is our wrap-up session. So series review, fun quizzes, and brainstorming next Wednesday, April 2nd at 11 a.m. Eastern Time and 8:30 p.m. IST. And thank you, everyone. And I'll turn it over to Sneha and Julia.
Thank you so much, Jolie. All right, I'll be sharing my screen. Is my screen visible?
Yes. Thank you so much, Sneha. Welcome everyone to today's session. Let's get started. Today we're talking about introduction to neural networks and deep learning. First, some agenda. We're talking a bit about timeline and history of AI, machine learning, and what brought us here to deep learning. First, we're talking about neural networks and its components, and then we're switching to deep learning and machine learning versus deep learning. So first, a little bit of history and timeline. In the 1950s, that was the first hype about artificial intelligence. This engineering of making intelligent machines and programs became the excitement of many researchers in the field. And AI, of course, leverages computers and machines to mimic the problem solving and decision-making capabilities of the human mind. And then in the 1980s is when the ability to learn without being explicitly programmed, it's when it took over and machine learning started to flourish. And machine learning is a branch of artificial intelligence and computer science, which focuses more on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. And then in the last decade, we can say that it's when deep learning is taking off, and that's what we're going to talk more about today. Okay, so what are neural networks? Neural networks are a set of algorithms that are inspired by the human brain, of how our brain works. They have this remarkable ability to derive meaning from complicated and imprecise data. That's where we use them the most. And we use them to extract patterns and detect trends that are too complex to be noticed by either humans or other computer techniques. That's why there is so much hype and so much excitement around neural networks. As you can see in like the image in the slide, for example, neural networks can be fed like a picture of a number, and it can detect which number it is. And we're gonna go like more in details about how it works, but just as a general focus, in this image in particular, our neural networks is fed an image of 28 by 28 pixels of number 2, and that's why we have 784 neurons, which correspond to each pixel. And at the end, we're going to talk about how neural networks work, but basically it has the ability to detect at the end that the number shown based on the pixels is a 2. So where do we use neural networks most? Like now you can see it used a lot in facial recognition, in signature verification and handwriting analysis. It's also very used in speech recognition research, in weather forecasting, in aerospace, which can be in, for example, in fall diagnosis or how autopiloting. And also it's used a lot in research in robotics. So artificial neural networks do mimic how our brain works. So think about our brain that generally when you open your eyes, what you see is called data, and it's processed by the neurons in our brain. and recognizes what is around you. That's exactly the same as neural networks work. Artificial neural networks take a large set of data. For example, in the image we took images of numbers and had to predict what number it was based on the pixels. It processes this data, draws out the pattern from the data. For example, in that example, it drew out the pattern of the number 2 and then outputs what it is. So let's talk a bit about a single neuron in our brain. Is the basic unit of computation in our brain, but also in neural networks, and is often called a node or a unit. It receives input from some other nodes or from an external source and computes an output. At each input has an associated weight, which is assigned on the basis of its relative importance to other inputs. And don't worry about this, we're going to talk a bit more and understand what are weights. And also the node applies a function to the weighted sum of its input. And no, this might be a bit complicated now, but we're going to cover it more in the following slides and going to make a lot more sense. So what are the main components of neural networks? First is the input units, that are the activity of the input units, represent the raw information that is fed into the network, and it's called the input unit or the input layer. And this is usually, as we said in our image that we had at the very beginning, it was like the pixels of the images were fed of the number 2 image that we had at the beginning. Then the second main components are the hidden units. Here we only have one hidden layer, one hidden unit, but as we're going to cover more in later, we might have a lot of hidden layers, and the activity of each hidden unit is determined by the activities of the input units and the weights on the connection between input and the hidden units. And finally, we have the output layer. Is the behavior of the output units depends on the activity of the hidden unit and the weights between the hidden unit and the final output unit. So for example, in the image that we had before, the output unit was the number 2, how our neural network detected that the image showed the number 2. And of course, the hidden layer is right now a bit of a black box for us, and we're going to cover it more in the next slides. And word to you, Shruthi.
Hello. Hi. Hey, everyone. Thank you, Julia. Thank you for the introduction. So let's look a little more deeper into what is deep learning. So like we shared before, it's basically a subdomain of ML, which is like using algorithms, using neural networks. And this is basically a combination or a complex structure of neural networks, like what we saw before, but imagine that put in a different, in a deeper stack or a higher breadth, and combining them in a more complex way to achieve more encoding of data and more feature extraction. So neural networks, and especially deep neural networks, are known to work better when you have larger data sets. These models have shown to perform better than the traditional ML algorithms. Okay, so 1 second. Sneha, can we go on to the next slide? Yeah. So here we see what a shallow neural network is and what a deep neural network is, right? So in the case of shallow neural network, we have an input layer, which is basically the input that we want. For example, how we saw in machine learning that the input is the number of rooms, the number of bedrooms in a housing prediction, and some features like that, right? So similarly, we have an input layer, which we have here as x1, x2, x3. Which we give to a layer that is a bunch of neuron. So we'll see deeper into what each neuron does. But for now, let's just abstract and think of that as a whole layer which computes something from our input. In here, in this case, we have one input layer, one hidden layer, and based on the computations that we have from this hidden layer, we are giving the output y cap. In case of the deep neural network on the right side, our hidden layers are multiple. Like there is a depth of them, and they are all multiplying, and they have their own structure and transformation of the input that we give. For example, here the x1, x2, x3 that we give to the first layer goes as the and the output that comes from the first layer goes as the input into the second layer. So it's getting transformed continuously to give you the output y cap in the deep neural networks. So in popularity, when we talk about deep learning, we mainly talk about the number of hidden layers that we are using, the type of transformation we are doing in neurons, and how that is used to give our output. Can we go on to the next one? Okay, now we'll see, now we'll look deeper into what each neuron does. So we saw that we have an input layer and we have a hidden layer, and each hidden layer has neurons. And like Julia mentioned, what the neurons are trying to mimic is our brain's neurons. So neural networks are, as I told you, are composed of many, many artificial neurons, and these are trying to mimic the individual neurons. So what does each neuron do? It gets an input. It gets some input from the input layer that we saw. And what we do is when we give this input to the neuron, we also multiply it with a weight. The weight, what does the weight do is basically it gives the importance to the input that is coming in. To just give an example, if for a house, we want to concentrate more on the number of rooms more than the square footage, then we'll have more weight added to the number of rooms feature than the square feet, and so on. So this is basically like a weighted transformation that happens at each of the neurons. So we have the input value, and we have a weight going in, and we also add some bias towards it, which is like how we do in linear processing. It's basically a factor that we use. So what happens, we have inputs, we have weights, and we have a bias, and these are all the weights and the biases are all configured as part of the learning process. So when these go into the neuron, it first uses a summation function, like how we see in regression. It multiplies your input with the corresponding weights and adds the bias. And once this is done, which it is represented as z, once this is done, we pass it to an activation function. So what does it signify? So in our neuron, in our brains, we have neurons, right, where we get a signal, but whether it goes on to the other ones or so is defined by a firing of the neurons, right? So basically, how does our information transfer in our brain? It goes to one neuron, which fires it to other neurons, and so on. So this activation function decides whether we are going to fire it out or not. Basically, it will have a number or a value which will signify signify basically, like, let's say a probability, or like say 0 to 1. The higher the value, higher the activation. Can we go on to the next slide? So as I said before, each input is multiplied by the associated weight, and then we sum all the terms and add the bias and calculate the output from the transformation function. And from the transformation function, an activation function will convert the result into what the neuron gives us output. So when we look at activation function, there are different choices that people use. So we can use a sigmoid function, which maps your output to 0 to 1. We can use a tanh function, which is basically the one that we are used to seeing in trigonometry, or we can use a ReLU function. Can we go on to the next slide? So here, as we see, so here sigmoid, tanh, and rectified linear units are like shown as example because these are some of the commonly used ones. So what is the rectified linear unit doing? It will basically take the max of your input, max of 0 and your input. So there are different reasons why people might choose one activation function over another, and that is not exactly covered in the topic today. But rectified linear units are something that most people prefer to use in a normal use case. Can we go on to the next slide? Yeah. So now we saw a little bit about what deep neural networks are, or what deep learning is about. So and what it composes of, and the main components that we have. And as mentioned before, the training and the learning process or the testing process, not the whole, is not covered in this topic as part of the ML series, but we will probably do it in the later series. But let's look at why we do deep learning when we already have machine learning. Like, why should we even do this? Like, why should we have so many layers and more complex structure? So just to define what machine learning and deep learning is, machine learning is a set of algorithms that parse data, learn from them, and then apply what they've learned to make intelligent decisions. So at the machine learning level, we are still having a lot of human intervention, and we are enabling the machine, but it is still machine-like algorithms or machine-like outputs. The processing or the input, or how we take the whole input or how we process it, still does not fully entirely mimic what we do as a human. So that's where deep learning comes in. Deep learning is also machine learning, because machine learning is a broader set of algorithms, which is just giving computer the power to learn without being explicitly programmed. So deep learning is a subset of machine learning that achieves the greater power and visibility by learning to represent the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts and more abstract representation. So what does this definition mean? So deep learning is basically trying to use neurons, the basic level of functioning and computation in our brain, and build it and try and mimic our human functioning more closely than many machine learning algorithms. And how it does is it builds a hierarchy of concepts. So what does it mean? So when we have a bunch of hidden layers, at each hidden layer, the input is transformed bit by bit. So in terms of computer vision, where let's take an example. So we have a lot of machine learning algorithms currently deployed in near traffic lights, which can do license plate detection, understand the speed at which you're coming, and understand if you're overspeeding, and so on. So what is it basically doing? It is first looking at your input and detecting feature by feature. So when we look at license plate detection, for example, first it might try to identify the edges and then understand how the edges are formed, and then slowly make up the pixel for each letter, and then combine them together to finally get the whole license plate, right? So it's basically doing it in a hierarchy of ways. So it is first getting a basic part of it, like edges, and then goes on to the arrangement of edges, and then goes on into a more deeper feature extraction level. So in deep learning, we are basically nesting these individual hidden layers together to basically get this transformation. Can we go on to the next slide? On looking overall at the difference between machine learning and deep learning, in machine learning, we have an input, and humans do more intervention as in feature extraction. Like, we do not just let's say we do not just give an image of a house and or some extra additional metadata and tell ask the uh, machine learning algorithm to just classify and tell whether how much the worth will be, or whether it's a modern house or an old type of house, like different types of houses, right? In machine learning, we have a little more feature extraction, and which goes into the algorithm, and then we get the output. Whereas in deep learning, this intervention is very less, and is not as dominant as in machine learning. And also, deep learning algorithms in general require less domain expertise as well, because they are designed to do the feature extraction. They are designed to understand the importance themselves based on the output that we want. So that's the main difference. So in a machine learning, if you want to decide detect whether this is a car or not, with an image, you give an image, to a let's say manual laborer, and then that person will extract the components and pass it as inputs to the classification algorithm, which will then give a car or not car as 0 to 1 output, let's say. In a deep learning, you're just passing the image, you pass the image, and then you get the output. The algorithm in itself will do both the extraction and the classification process. So to differentiate machine learning and deep learning a bit more, as we saw, machine learning has a rather simple structure, while deep learning is more complex and intertwined. To achieve a great performance, in most cases, you need a lot of hidden layers, and you need a lot of depth, and the number of neurons at each layers could also vary. So it's more complex and it's more intertwined. In machine learning, due to its simple structure and also able to put it in the depth or like the breadth, we are able to easily interpret what's happening. And even for big decision trees, we are able to visualize till a decent point of range. Whereas in deep learning, one particularly difficult problem that people face is to understand what it is doing at each level, because we saw that once we get an input into one hidden layer, it gets transformed continuously. So when the output comes, or the last hidden layer, understanding how the input got transformed is more difficult and very more hard to visualize than in a traditional machine learning program. This is something that is being constantly worked on recent days on interpretation and interpretability and basically explainability of a deep learning model, but it still has a long way to go compared to what we have in machine learning. And like we saw, machine learning needs more manual inputs and selections, while deep learning does not need as much manual intervention. And another thing is machine learning works better with let's say a smaller data set when compared to deep learning. Even in machine learning, we don't want a very small set, like we talked about before, that it has its own issues, and it has its own training needs. But when compared to machine learning and deep learning can work with millions and billions of data better than machine learning. And it also suits better because we don't have to be transforming or extracting like features for those million or large data sets by ourselves, as we might have to do in machine learning, in deep learning. So another main important thing is machine learning works very well when you need something with domain expertise, or when you have something specific that you want to achieve. Like, I want this algorithm just doing this much, and I can let you know what is important and what is not. Deep learning is more suited for abstract things that we ourselves are not able to explain. Like when we just look at something, like Julia mentioned, when we look at data, what it is that we are exactly looking at, we do not exactly think about it. Like when I, let's say, look at this computer, or let's slide, what features does my eyes or my brains notice first? I'm not really sure. Like that's actually a research topic on its own, where they look at which they try to blur some features and show only some features and see if this is what people notice first. So we've seen to notice like the shapes, we are known to notice the colors and so on, but how exactly, which one exactly goes through is something that is at a more deeper level, right? So that we do not often think about. So when you have a more abstract problem, deep learning is much more suited. But when you have a more domain expertise, and when you want a particular a specific functionality, or when you know what it is that you want, machine learning is better suited. Also, deep learning algorithms in general, because they do their own feature extraction, can be used for different use cases. For example, if you train, like I said, for the traffic lights, if you train the model to extract features from cars, it can be used for multiple of applications. Like it can be used for license plate detection, it can be used for car classification. So you are changing the final classification layer, but the feature layer can still remain the same. And this is something that we use in deep learning these days. Like this is called transfer learning as well. Like you use already used trained a deep learning for some other purpose, and you use that for a different application. So that's majorly the main differences between machine learning and deep learning. Over to Sneha for the poll.
Before we get to the poll, Shri, we have a couple of questions.
Okay.
Okay, first, there was a question about how many hidden layers are needed. How do you figure out the architecture of the neural network? Very sadly, we don't have a generic way to determine like how to build a neural network, or like the number of neurons we need, the number of layers. Usually, like how we do it, like based on the problem that we have. But usually based when we see the problem, sometimes we do start with a rough guess of prior experience that we've had, or about like different neural networks that have worked before, or for similar problems. There are like a couple of neural networks that are also whose architecture is known, and we also might try them first. But it also this depends on a lot more features that we haven't really covered in today's session. That is a lot more in depth to neural networks, but this relates to hyperparameters too. But usually what I would suggest is to start your neural networks simpler, and then start building complexity from to see like what would work more for your problem. But I would definitely suggest to start with simpler, less layers. And then, of course, it also comes with experience, and that's how usually it's done. Also, like some activation problems can work better for some layers. Activation functions can work better for some layers, depending on the problem as well. And these are all things that come with experience. But unfortunately, neural networks are still kind of a black box. So there's no, unfortunately, any generic way to build the perfect architecture for your problem. I don't know if that answered your question. Shri, if you want to take the other question, it's about deep learning, I think.
So, Stacy, there have been some ways, you can understand how you can visualize each hidden layer and see how it is combining. But yeah, to exactly know, it'll need a little more I'm little more understanding of how the transformation is working to actually see which is determining which feature is more important. Just at a higher level, you won't be able to understand because it's getting transformed a lot. Yeah, there are lots of different types of neural networks. There is ResNets, there is there are main types of neural networks. Like there are some that are used for vision majorly, like convolutional neural networks, and there are different types of convolutional neural networks. And then we have sequential networks, which are more commonly used for text processing, and there is a bunch of different architectures in that end. And there are others which are used for reinforcement learning. So there are a lot of architectures in deep neural networks. Over to Sneha for the poll.
Thank you so much to everyone who is filling out the poll right now, but also if you have any more detailed feedback on this session or any session of this series, please feel free to let us know in our Slack channel. Any suggestions as well, because we're going to do more series. And I see also a question in the Q&A box about further details, and we might do a more in-depth series. So if you have any suggestions, please do let us know. Thank you so much, everyone, for joining us today and also throughout the series. As we said, if you have any other questions on this topic or any other, please feel free to reach out on our Slack channel and ask all your questions. As we said before, also, if you have any suggestions for future series, also do let us know. And also check our Slack channel for everything, all the exciting series that we're planning next.
Thank you so much, everyone, for attending today. And thank you all so much for helping us by answering the poll. So if you have any questions, do ask us right now. Others, we've come to an end of this session. And we'll be having another session next week. That's going to be kind of like a closer session where it's mostly going to be a quiz. So you can join in, and it's going to be a fun session where we'll have quiz questions so we can see who is able to answer the most questions. And you'll even be featured on our social media if you are able to get lot of answers. So do join us next week at the same time for that session. But as for this session, it's ended, and thank you all so much for your participation. So if you do have any other questions, do feel free to ask us. Otherwise, the session has ended. Thank you.